Most people think of a vacuum as nothing, an empty stage where nothing can happen. But in particle physics, a vacuum is more like a field that still has energy. And sometimes the nothing is unstable. The most unsettling idea in modern cosmology is vacuum decay. Our universe could be sitting in a false vacuum, a low but not lowest energy state. Then, a tiny bubble of true vacuum could appear and expand, rewriting the rules everywhere it reaches. The misconception is that this would require a cosmic catastrophe waiting politely at the edge of time. The open loop is stranger. What exactly starts the switch? What happens inside the bubble? And why does the expansion create something like an entropy burst instead of a quiet, reversible change? If the vacuum can decay, what does that say about stability, thermodynamics, and even why there's so much disorder, so much entropy in the universe at all? To understand the before, picture the landscape of possibilities in quantum field theory. Fields can have multiple energy minima. The state with the lowest energy is the true vacuum. A higher local minimum is a false vacuum. It's metastable, like a ball resting in a shallow valley separated from the deeper one by a hill. Classically, the ball stays put. Quantum mechanically, though, there's a non-zero chance to tunnel through the barrier. This idea matured as physicists tried to explain the early universe, inflation, and the observed smallness of the cosmological constant. During inflation, scalar fields could have been trapped in a false minimum. After reheating, the system rolled toward a lower energy state. But even today, the same mathematics implies that, in principle, our current vacuum might be false, waiting for a rare quantum event. The question wasn't whether bubbles could exist in theory, it was how they form, expand, and how that expansion connects to entropy and the arrow of time. The core mechanism starts with the idea of a bubble as a region where the field has made the transition. Imagine a field value that characterizes our vacuum. In the false vacuum, the field sits around one value everywhere. To create a bubble of true vacuum, the field must fluctuate so that, in a localized region, it climbs the barrier and lands on the lower minimum. Quantum tunneling tells us that this transition prefers a particular shape, a roughly spherical critical bubble. Too small and surface tension-like effects pull it back into the false vacuum. Big enough, and the system finds it energetically favorable for the bubble wall to accelerate outward. The mathematics describes this with an instanton solution, an imaginary time trick that turns tunneling into a kind of boundary value problem. The result is the bounce action, which controls the probability per unit volume and time of bubble nucleation. In other words, the universe doesn't wait for the vacuum to choose globally. It can happen locally through rare nucleation events. Once nucleated, what happens to the interior? The bubble contains true vacuum, with different vacuum energy and potentially different particle masses and interaction strengths. The wall separating inside and outside is where gradients and energy concentrate. As the bubble expands, it converts vacuum energy into kinetic energy of the wall and, crucially, into excitations of fields as the wall passes through regions of space. Those excitations are the route to the entropy burst. Even if the underlying transition is quantum incoherent at the microscopic level, the expanding bubble creates conditions for particle production, reheating of modes, and phase mixing among degrees of freedom. Entropy is not created because the math adds disorder arbitrarily. It rises because information about the initial localized fluctuation becomes inaccessible when you average over enormous numbers of microscopic states in a rapidly evolving, non-equilibrium setting. The arrow of time is encoded in that conversion. Energy flow from a structured vacuum configuration into a bath of excitations with many possible configurations. There's also an intuitive energy accounting. In a false vacuum, the energy density is higher than in the true vacuum. When the bubble expands, the net energy difference becomes available. If the true vacuum is lower, the outside loses energy density while the wall and the produced particles carry it away. The expansion can be thought of like popping a bubble in a sealed pressurized fluid. Once the interface forms, the pressure difference drives rapid outward motion and generates waves, turbulence, and heating. Here, the waves are quantum fields excited by the moving boundary. Historically, the idea of vacuum decay grew alongside studies of false vacua in the context of spontaneous symmetry breaking. And it later became central to inflation models, where the universe might have been stuck in a higher energy state. The phrase entropy burst isn't a single textbook term, but the concept is natural. Any vacuum-to-vacuum transition that releases energy into excitations will drive a fast rise in entropy as the system departs from equilibrium. When bubble walls sweep across space, they can initiate particle production similar in spirit to reheating, but localized and causal, rather than spatially homogeneous. The broader implications are where the stakes become cosmic. First, vacuum metastability places a probabilistic lifetime on our universe's ground state. That changes how we interpret constants of nature. They might reflect where we are on an energy landscape, not a fundamental, unchangeable truth. Second, it reframes inflationary scenarios. If our universe once experienced a false vacuum, then bubble nucleation and growth are not abstract toys. They could have been mechanisms shaping the early cosmos, potentially leaving imprints like non-trivial large-scale structures or distinctive signatures in perturbations. Third, it ties directly into thermodynamics. Entropy burst behavior connects vacuum decay to the arrow of time because entropy increase tracks the conversion of vacuum energy into many particle degrees of freedom. In practice, it suggests that even events triggered by quantum tunneling, which sounds reversible and sterile, can still produce macroscopic irreversibility once expansion and interactions take over. Finally, vacuum decay influences how we think about nothing. If the vacuum has energy and can transform, then empty space is not a passive backdrop. It's an active state of matter with dynamics. Our universe's stability becomes a question about field configurations and quantum probabilities, not merely about whether space is occupied. That has philosophical weight, but it also has technical consequences. It forces physicists to compute decay rates, wall dynamics, and non-equilibrium evolution to assess whether false vacua are consistent with observed cosmology. So the journey is this: a vacuum isn't truly empty. It's a field held in a metastable energy minimum. Quantum tunneling can nucleate a critical bubble whose size decides fate, shrink back to false vacuum, or expand to convert true vacuum across space. The expansion releases vacuum energy into particles and excitations, and because that process scrambles information among countless microscopic configurations, entropy can surge, producing a burst-like rise associated with rapid non-equilibrium evolution. The mic drop is that the universe's laws are not guaranteed forever. They can switch domains through a quantum event, so local it starts as a fluctuation, then becomes a macroscopic rewrite. Subscribe if you want more stories where the cosmos turns out to be stranger than nothing.